Okay, so welcome everyone. Today we are going to discuss uh, a continuity of a function on a real value function, uh, some properties of that continuous function, limit of functions where we will also discuss, and then we will also discuss the uniform continuity of a function. So we will see how it goes, and if you have any question in between, you can ask that too in between. You can unmute yourself and ask questions. Feel free to do so. Okay. So without a further delay, let's start. So again, hello everyone, I'm Prerak from Aizer Bhopal, and I weekly conduct these sessions with you guys. This is another 2 hour long live discussion session, and recording of these sessions will be available on the YouTube channel Maths with Prerak. So you can so this recording will be uploaded by tomorrow morning. You can go back and check for it, and the previous recording you can also check on this same YouTube channel. Okay, so before we discuss exercises, if you have any doubt or questions you want to discuss, you can either write it in the chat box or you can unmute yourself and ask directly to me. I hope I'm audible clearly to you. If I'm not audible clearly, please uh, mention that. Okay, so let us discuss this question number 0.1, which is in which we need to find out the limit of the function. Okay, so in this case, you can see in the first part of the question, you can see that the limit is a bit different. It's not directly tending to one; it is tending to one plus. So first of all, let us see what does it mean. Uh, what does it mean to x tends to one plus, and then we will try to see the limit of the function. Okay, so clearly this function uh, fx, we call it to be fx xy x minus 1. This function clearly is not defined on x equal to 1. Okay, because the denominator at x equal to 1 will be 0, hence the function will not be real valued at 1. So it is not defined on x equal to 1. So this function is defined on domain which is r minus 1, and it is taking real value, so it is a real valued function on a real value. Okay, so this function we are considering now. In this question you are asked to find out. Okay, so we are discussing the a part, so let me write that question again for you. So we are calculating limit x tends to 1 plus x over x minus 1, and this function is defined for x being not equal to 1. Okay, so what does it mean? So first let us see what does this mean. Okay, this means that if you draw the real line, okay, if you draw the real line, let us say this is the real line, and if you draw these points, let's say this is 1. So you can clearly see that there are two ways to approach 1. You can either approach from the left hand side, or you can approach from the right hand side. So there are two ways to approach 1. What do I mean by that, approaching to 1? Because when I say x tends to 1, it means that values uh, are getting closer to 1, and it can get closer to 1 from on real line in two ways. It can get closer from the right hand side, it can approach from the left hand side. Okay, so when we say it is 1 plus, so that means it is uh, so that means the values that are so we can say that values that are approaching from the right hand side can be also think of as 1 plus h type. Okay, if you are approaching from the right hand side, and if you are approaching from left hand side, so your value is smaller than 1. So in that case we say it is 1 minus h. Okay, and we say that h uh, tending to 0. Okay, so now when we say that it is x tending towards 1 plus, that means it is 1 plus something. Okay, we say it to be h. So x is taking this value, x equal to 1 plus h. That means as x is approaching from this left hand right hand side. Okay, so x is going to take this value. So you can rewrite this whole limit in terms of x equal to 1 plus h, whenever you have x tending to 1 plus limit. So x tending to this 1 plus can be also write it as h tending to 0, or x plus tending to x, okay, um, which is also same to say that h is tending to 0, and you replace your function with to be this x plus h value. Okay, so that's what we are going to do in this case as well. So if I do that, my limit function will so this limit x tending to 1 plus, this become okay, and moreover I made a mistake over here. This x will be then 1, and it is approaching to 1. Okay, this will be 1. Yeah, that's what I wrote over here. It will be 1 plus, so it will be 1 plus h. So the function value will be 1 plus h in this case. Okay, so this, if you do the calculation, it will turns out to be h plus 1 by h, which is nothing but 1 plus 1 over h. Okay, and now you know, again you can, if the limit of both of the function exists, then you can write it as the sum of the limits. But in this case, you can see that limit 1 over h, limit of 1 over h function doesn't exist. Okay, because as h tends to 0, this 1 over h goes to infinity. So this limit does not exist. Okay, is this clear? So I repeat the argument. So in this question, we have given that the limit of limit x is tending to 1 plus. Now, what do we mean by 1 plus? 1 plus is you are approaching 1 from the right hand side. That means your x looks like 1 plus h. Now you replace your x in the function to be 1 plus h, and you solve for h tending to 0. So that's what I did, and the limit, we concluded that the limit that we uh, that we got in the end doesn't exist. So this limit does not exist. Okay, so this does not exist. Okay, now what about the limit b that we have on the left hand side? So let us write that too. Okay, so in this function as well, you can say directly that the limit doesn't exist. Okay, but there is another way that we will use the first part to say that the limit does not exist. It's because if limit at x uh, tending to 1, if the limit of this function, sorry, so if limit x tends to 1 of this function exists, then it must be equal to that, which this implies that limit x tend to h minus and limit x tending to h 1 plus, both of them exist. Okay, and we have seen in the first part, so in a we know that limit x tending to 1 plus of the same function does not exist. So we can conclude that this limit of x tending to 1 also does not exist. Any question? Any doubt? Okay, if there is no doubt, we can go ahead and discuss the next question. Question point two. So in this question also we need to. So let's say this is the first question. This is the second question in this point two question. So in both of the question, you need to calculate the limit when x tends to infinity. Okay, so let us discuss the first part. Limit x tends to infinity. Okay, so this, since x is tending to 0, so the idea is to use the fact that 1 over x of x tending to 0, limit of this function is equal to 0. Okay, so the idea is to use this equation. And how do we get that? So we can see that in, this is a fractional function, this is a fraction. Okay, and in this fraction, uh, it's x, square root of x is in uh, is in linear equation. Okay, in both of the, in denominator and the numerator as well. So we want to convert this into 1 over x type factor. So as x tends to infinity, this will be equal to 0. We can use this fact. We can use this limit. Okay, so the idea is to um, use this limit. This is the idea. And how do we do that? So it is simple. I think you can also guess this method, the solution. Okay, so the idea is to just take square root of x common. So you will get 1 minus 5 square root of x divided by 1 plus 3 square root of x. Okay, now we want to, now you can divide, now you can cancel square root terms, and what you are remaining with is, this part. So in this part you need to calculate the limit. Now the limit of this function will exist if the limit of this function will exist if the limit of the numerator exists, limit of the denominator function exists. So, and so limit x tends to infinity of 1 minus 5, this square root, is going to be 1. Why? Because the limit of 1 over 5 square root of x is 0 as x tends to infinity. Similarly, limit of x tends to infinity of 1 plus 3 by square root of x is again going to be 1. So this whole limit is going to be 1 as x tending to infinity. Okay. So here we are using the fact that limit of, if the limit function is given to be in a fraction form where the numerator limit exists and the denominator limit exists, then the limit of the fraction is equal to the limit of the numerator divided by limit of the denominator. Okay, is this clear? Okay, so let's move on to discuss the next second question. So it is a square root of x minus x divided by square root of x plus x. Okay, so again in this question, we take x common. Okay, we take the higher degree term common. Okay, so it will be 1 over square root of x, correct, minus 1 divided by x, again 1 over square root of x plus 1. This x and x get cancelled, so we are left with 1 over x square root minus 1, 1 over square root of x plus 1. And as I apply the limit x tending to infinity of this thing, this is equal to minus 1. Similarly, limit as x tends to infinity of 1 over square root of x plus 1, this is equal to 1. So since both of the limit exist, limit of the numerator exists, limit of the denominator exists, so the limit of the fraction function also makes sense. So it turns out to be minus 1. Okay. This question also similar to the previous question, so I don't think uh, this is anything new for you, and I think you already are familiar with such kind of computation with limit. Okay, so let's move on to discuss this third question. So this third question is on the uniform continuity. So before going to uh, prove this question whether it is true or false, let us first recall the definition of a uniform continuity. Okay, so um, the definition of uniform continuity. So we say a function is said to be uniform continuous. A function f from R to R is said to be uniform continuous at a continuous on an interval on some subset on some open interval, let's say interval, it's fine, on a b in R, if for epsilon greater than 0 there exists delta depending only on the epsilon, such that fx minus f of y is smaller than epsilon for all x minus y is smaller than delta. Okay, for all x y satisfying this property on this interval ab. Okay, such functions are called uniform continuous. Some simple example to them, to the uniform continuous functions, are the identity function defined to be fx is equal to x. Okay, um, then these function constant functions, uh, and so on and so forth. So there can be yeah, so functions of the type I of this type of function where this is bounded by some constant times this thing for all x y in R. Okay, such kind of functions. So these are the pretty standard examples of uniform continuous functions. Okay, so is the definition clear? Is it, are you able to recall the definition? Okay, so now in this question you need to prove that you have given a function of a real value, the real valued function on a real variable, and you have given a positive constant satisfying this inequality. for all xy in R. So now you have to prove that f is uniform continuous. So here we assume that it is asked us to prove that uniform continuous on all of R. Okay, when it is not given, you assume it to be it is asked to be proven on the whole set R. If it is given, if they are specifying the set, the subset of R, then you need to prove on that subset. Okay, so f is a function from R to R. Beta is a constant, positive constant. Satisfy this inequality. You need to prove that it is an uniform continuous function. Good. So for that, let me just write down the inequality that the function satisfies. This is more than x minus y to the power beta for all xy in R. So for those who are not familiar, this is a symbol for all in mathematics. Okay, so whenever you want to write for all, you just draw this uh, symbol. Okay, so now you need to start with let's say for epsilon, for given epsilon, you need to find delta which is depending completely on epsilon, such that this thing happens, that f of x minus f of y is smaller than epsilon whenever your x and y is smaller than delta epsilon on R. Okay, so how do we prove that? So for that, we will use this inequality that is given to us. So first we start with assuming that fx minus fy is already smaller than epsilon. Okay, or maybe better, we start with this inequality being assumed. Correct. Now you want to say you want to find out a delta for which this modulus is smaller than epsilon. So let's say this is smaller than delta. Sorry. Um, yeah. So let us say this is smaller than epsilon. This whole thing is smaller than epsilon. Then this thing will be smaller than epsilon. So or better, you can assume that this thing is smaller than some, let's say delta, or let's say some delta is fine. Okay, so then what happens that this modulus will be smaller than delta to the power 1 over beta. Okay, and now you want your fx minus f of y to be smaller than epsilon. So it is better to take this thing as your epsilon. So when this will be smaller than epsilon, so this whole thing will be smaller. So what I'm saying, you take your delta to be epsilon to the power 1 over beta. Let me write it more in a better notation. So assume this is smaller than epsilon. You want to find out the beta, delta. So write it x minus. So x minus this modulus is smaller than 1 over beta. Okay. So you choose this to be your delta. Okay. So for this delta, this whole thing will be your function modulus will be smaller than epsilon from this inequality. So you can rewrite this. So take delta to be epsilon over 1 over beta, then your function fx minus fy is smaller than epsilon whenever your x minus y is smaller than delta. How? Because when x minus y is smaller than delta, so if you take the power beta over it, this will bound on the function modulus. Correct? And now this thing is what? This is epsilon. So this thing will be implied. So whenever you assume this thing is going to happen. In other words, you have found out a delta completely depending on epsilon, for which this condition is being satisfied. Okay, so you were asked to find out delta. such delta. You have found out such delta in terms of epsilon. Uh, this proves that your function f is uniformly continuous. Okay, so any question in this? Hello. Yeah. If it is clear, we can move ahead and discuss the next question. So, then this is true. Okay. So this is true, and we have given a proof of it, and this is the proof of this. So whenever you have such kind of inequality on the function modulus by the value modulus, by the x modulus, so you just need to find out appropriate delta in terms of epsilon, which you will get from this inequality. So it's not that hard. It's simple. Okay. Okay. So now let's move on to this question, which asks you to find out that can f be defined on x equal to 2 in such a way that the function f is continuous. So if you were there in my last recording session, or if you guys have seen my last recording session, so in that session I have discussed about something which is called removable discontinuity. Removable discontinuity. Okay, so I have talked about something which is called removable discontinuity. So where the function is not continuous at a point, but you can remove that discontinuity and give it an appropriate value to make that function to be continuous at that point. Okay, so a simpler example to that is a function uh, which is like this. So this is my, let's say I'm drawing the graph of the function. Okay, so let's say this is my function. It is being constant till this point, and at x equal to 0 it is not defined, and then it is a line. So at x equal to 0 it is defined to be 1 or 2. At x equal to 0 it is defined to be 2, and uh, this is the graph of the function fx, which is when x is negative you have defined it to be x equal to 1, and when x is positive you have defined it to be it is shifted in the plus side. So when it is 0 it is taking minus, it is taking plus 1. Okay, so x minus 1, sorry, x plus 1. Okay, so in this function, and when x equal to 0 you define it to be 2. So this kind of function, you can see it is continuous, but at origin you have made this function is discontinuous. Okay, except x equal to 0 it is continuous throughout the domain, throughout the R. So you have made it discontinuous. Okay, so how do we remove this? So in some way, if you can remove this discontinuity, then this function becomes continuous again. That's what the idea is. So can you do that? Yes, you can do that. You can remove this discontinuity. You can define uh, your f at 2, sorry, f at 0 to be 1 instead of uh, instead of 2. Okay, so then this function will become continuous at origin. So such type of discontinuity is removable discontinuity. Now we come back to the question. So function is defined to be for all x except 2 by this function. Can f be defined at this point so that f become continuous at 2? Okay, so the idea usually here is to, so as I have previously mentioned, that you can approach your function uh, okay, as I mentioned previously also, that you can approach a function value. So it is given that x equal to 2, it is not, so at x equal to 2 this function is not defined. So So you can approach your function from the left hand side and then or from the right hand side. You can approach function from the left hand side or from the right hand side. Okay, and we say that if you are approaching your function from the left hand side, then we say the corresponding limit, we define the corresponding limit to be x tending to 2 minus and your function. And if you are approaching your limit from the right hand side, you say it to be x 2 plus. Okay, so we call this to be left hand side, left hand limit, and this to be, we call it as right hand limit. Okay, and when both of the limit, in short we can write it as LHL and RHL. If both of the limit are equal to each other, then we can define our function to be, then we can define f at 2 to be that limit. Let's say this is a, so we can define it to be a, and by this LHL being equal to RHL, this condition that x tending to 0, x tending to 2 is equal to a, which is f of 2, which this will be equal to a, which is nothing but f of 2. So it is continuous at f, continuous at 2 also. Okay, so in order to so if I come back to this question, so in order to say that this function, if this function can be defined a continuous at this x equal to 2 point, okay, if we can so then we need to show that its RHL limit and LHL limit make sense. Okay, okay, so let's come back to the function given. So f is given to be, f of x is given to be x square plus 6 or 5, it is x square plus x minus 2. Okay, x square plus minus 6 divided by x minus 2 for x not equal to 2 and x equal to 2, it is not defined. So it has natural discontinuity at x equal to 2. So now in this case it is simpler. I don't think we need to go into LHL and RHL, that kind of stuff, because you can see that this function, because you can see the fact you can see that quadratic polynomial that we have in the numerator can be factored into x minus 2 times x minus 3, x plus 3. Sorry. Okay, you can factor this into this, and as you divide this by x minus 2, you will get x plus 3 as the resultant. So this function is not actually meant to be discontinuous at x equal to 2. Okay, you can actually define this function to be, but the representation of the function make it look like that it is discontinuous at x equal to 2. So this function can be made into continuous, because this function, which is fx is equal to x plus 3, this function is a continuous function on all of R. Okay, so and what is at x equal to 2, it is 5. So you can define this to be the limit. Okay, so you can define, so I define a new function, define g of x, which is equal to fx whenever x is not equal to 2, and you define it to be 5 when x equal to 2. Okay, and clearly, because this clearly gx is nothing but x plus 3, so it is continuous, hence continuous at x equal to 2. So the extension is continuous at x equal to 2. Yeah, so I hope this is clear to all of you, and the argument also makes sense to you. This kind of discontinuity is called removable discontinuity. You can remove the discontinuity from the function definition, and you can make your function to be continuous. Okay, so this is actually quite easy, uh, and it doesn't require this LHN and RHL method. But this is also another way to make function continuous when it is not uh, at some certain points. Okay, so this completes our discussion on this question number 4. Any question? If there is no question, then we can move ahead and yeah. So if there is no question, then we can move ahead and discuss this question point 5. So in this question, you have given A, B, C in an increasing order, and suppose that F is continuous on the closed interval A comma B, and G is continuous on closed interval B comma C. And on the boundary or the intersection of these two intervals, which is at B, both functions are equal. Both functions take the equal value. You define the third function h to be on the interval A comma C, and you define it to be fx on the first interval AB, and you define it to be gx to be the rest of the interval BC. Now you need to prove that f is continuous on A comma C. Okay, so now we know that continuity um, continuity of a function h is a pointwise phenomena. What do we mean by that? We say h is continuous at a point. Okay, so I can break this into case wise. So we say, so case number 1, uh, yeah, so I need to prove that h is continuous on this interval A comma C. Okay, so I can break this into 3 cases, okay, which can be written it as A comma close open B at B, and then uh, B to C. Okay, so yeah, so this on the first domain we will call it to be case 1, second we will call it to be case 2, third we will call it to be case 3. Okay, now on case 1, clearly uh, when you take x in this interval, okay, your h of x is nothing but f of x. Okay, and we know that f is continuous at x, where x is taken in this interval. Okay, similarly for case 2 also you can argue in a similar manner. If you take x to be in this interval, your hx is nothing but gx. So we know that uh, g is continuous for any point taken in this interval. Okay, now the only problematic point you may find is when x equal to b. So that's the only interesting point we need to look into. So what is the definition of continuity? So for epsilon greater than 0, for given epsilon greater than 0, you need to find there exists delta greater than 0 such that fx for all x minus p smaller than delta. Yeah. So I can, yeah, it is better if I draw the real line. So let's say this is my real line. Okay, so in this real line, let's say this is my point B, this is my point A, this is my point C. Again, I'm approaching from two directions, one from the left hand side, another from the right hand side. Okay, so this is my, let's say, domain. This is my delta radius domain. Okay, so in this delta radius domain, you can notice that if your x is x belongs to this part. Okay, so then it is part of this interval, and the function uh, hx will be fx. Okay, so in other words, first you need to say that, okay, this is, I think this is fine, and when you take x from this interval, then this will be part of this interval, making hx being equal to gx. Also, we say that limit of a function, just recall the definition of continuity at a point. uh, we say it to be continuous if this limit exists. Okay, and if this limit exists, let's say equal to some c, and this c is nothing but f of p. Okay, these are the two conditions that we need to follow. Okay, so before going into these two conditions, so let us see what is this limit. So we have seen today that this limit of x tending to b of fx is similar to the limit we approach from the left hand side and limit we approach from the right hand side. That means x equal to b plus of fx equal to limit x equal to b minus. Okay, now what is, now we will look into these two limits, which is rhl and this is lhl. Now what is rhl in this case? So it is limit x tending to b plus of fx, sorry, hx everywhere it is just hx only. uh, I wrote it as fx, so my apologies for that. Now what is v plus? So v plus means I am approaching from uh, left hand side, so that means my x is like b plus h type. Okay, and h is approaching to 0, so this will imply that my function fx, which will be b plus h, will be what, will be type of gx. Okay, so now this will be limit h tends to 0 of, now we know that this limit is equal to g of b. Why? Because g is a continuous function at b, so this is equal to this. correct? Now similarly, what about the RHL limit, LHL limit when we approach B from the left hand side? So again, in this case, notice that x is nothing but B minus h, and h is approaching to 0, implying hx to be equal to uh, h b minus h, making h to be f b minus h. So this limit will be equal to, which is nothing but f, and now again limit of f, because f is continuous, f is going to be continuous at b also, so it is nothing but f of b. So now the question is, r is LHL is equal to RHL, and the answer is yes, it is. And what it is? It is equal by the assumption given in the, that hx is equal to gx. Sorry, that fp is equal to gb. Okay, with this assumption, uh, we can apply this assumption over here to say that this RHL is equal to LHL. Okay, and now once these two are equal, you can define this limit at x tends to b of hx, and this limit is nothing but turns out to be hb only. So hx is continuous, implying hx is continuous at b. Okay, let me write it here, whatever I said. Now this implies that limit of x tends to b of hx exists and equal to f of b, which is h of b, which is g of b. Hence, h is continuous at b, implying h is continuous on a comma c. This completes the proof of the result. Hence, this is true. Okay, is this clear to all of you? Any question, any doubt in this? Okay, if it is clear, let's move on to the next question. Question point 6. So in this question, you need to prove that the function of absolute value function is continuous at every point c in R. So how do we define absolute value function? First of all, let us first look at how do we define it. So fx is equal to x if x is positive. It is equal to minus x if it is negative. Okay. Yeah. So this is how we define. And if you try to look its graph, so the graph will look like this. So this is how the graph will look like. This is y-axis, this is x-axis, and this is the graph of mod x. This is origin. Okay. So this is how the actual function value graph will look like. Okay. So you can see, uh, like from the picture also sometimes it's very clear that continuity makes sense. Okay, so in this figure also, in the graph also, you can see that if you try to draw this function, you can draw this function without lifting your pencil or pen from the document, lifting up your pencil or pen. Okay, so that's why it is clearly, you can see like intuitively it's a clear, it's a continuous function. So intuition is important to start with, but you need to prove it mathematically also. So how do we prove it mathematically? So again, we go back to the definition. We try to see where are the problematic points, and where it is fine to uh, go ahead. So we will. Um, so let's say we prove the continuity in three cases again: when x is positive, when x is negative, when x is positive. Okay. So in this case, the modulus function is equal to x only. Okay, so we call it to be fx. It is just this only. So now we start with epsilon. For epsilon, fx minus, so we prove continuity at, let's say, some point. So for, so at point x naught in 0 to infinity. Okay, so that means fx minus fx naught smaller than epsilon for given epsilon greater than 0. You need to find out a delta so that this happens. So now this is clearly this function. If I rewrite it, this function is clearly this x minus epsilon naught. So take your delta to be epsilon only. Okay, so in this case, so this implies that, so if you take this epsilon delta to be epsilon, then this function f is continuous at x naught for all x naught in this open domain. Okay, is this clear? Okay, now what happened when I say when x is negative? So in this case, my function f becomes minus x. Okay, uh, the modulus x become minus x. So again, I go back to the definition, and I prove the continuity. So continuity at x naught in this minus infinity to 0 domain. So again, I start with this thing being smaller than epsilon for, let's say, for some given epsilon greater than 0. I say this happens. Now I need to find out a delta. Okay, what is that delta? So delta I will find out if I rewrite this. So what is fx? Fx is minus x. What is fx naught? It is going to be minus x naught. So this will be, this is bracket I need to use. I haven't used the bracket. So it is going to be similar to x minus x naught. Okay, you can just take the minus common and modulus will modulus sign will remove the minus. Okay, so this will be true. And yeah, so this is smaller than epsilon. So again, you take delta to be epsilon. Okay, so take delta to be epsilon, proving, implying that this uh, fx is continuous at x naught in this. Okay, now the remaining cases when x equal to 0. So let's say when x naught is equal to 0, so we start with epsilon, and now we need to prove that fx minus 0 is smaller than epsilon. Now what is fx? Fx is mod of x minus 0, which is similar to mod of x, modulus of mod of x, which is again going to be mod of x, because positive value of modulus of positive value is again that value only. Okay, because mod of x is positive. So this thing is smaller than 0. Again, you take delta to be equal to epsilon. So uh, your modulus function, so fx, which is modulus of this, continuous at x not equal to 0. So this completes this case as well. Any question? So now we move on to some proving some theoretical questions which have more theoretical approach to problems. So before that, if you have any question in these questions that we discuss, you can ask now. Okay, no question. Then let's move ahead. So this is a theoretical question, and I think it's from your assignment, but I'm gonna solve it. So this is given to be a function. You have a real valued function. You have a real valued function on real variable. So you have given a function, and you need to prove that the following three statements are equivalent to each other. So what do we mean by that equivalent? That if you assume A, you can prove that B is true. Okay, and if you assume B is true, you can prove A is true. Okay, this implies that A is equivalent to B. Okay, and now by saying that, and if you can say similarly that A B, assuming B, you can say that C is true, and assuming C, you can say A is true. Sorry, B is true. Then this implies that B and C are equivalent. Okay, and when you have these two equivalences, you can say that A is equivalent to B, which is equivalent to C. Okay, in other words, all three statements are equivalent. Okay, so that's what we are going to do. We are going to follow this approach. So first we will prove this part. Okay, then this will be our first step. Then we will prove this part. This will be our second step, and then I will use this third fact to prove this final result. Okay, so 1 2 3, these will be our steps today. These will be our steps to prove this question. Does it make sense? So what I'm saying, that these three statements are equivalent to each other. Okay, so that means the A part is true. All three options are false. So we will prove the A option. That means all three are equivalent, and we will follow this approach. First step, second step, third step, giving us the final desired result. Okay, so again, let us. So we start with statement A. So statement A says f is continuous f is continuous function. Okay, this is what statement A says. So f is a function from R to R, and it is given to be continuous. So what do we mean by continuous function on f? Let us quickly recall that. So we say f is continuous at x naught in R if f of x belongs to f of x naught minus epsilon, f of x naught plus epsilon, uh, for all x naught belongs to x belongs to x naught minus delta. So if for every epsilon neighborhood of fx naught there is a delta neighborhood of x naught, okay, such that okay. So so why I'm using these delta or epsilon neighborhood type of, why I'm using the neighborhood type behavior, you will see it uh, in a few minutes why I'm using these notation, why I'm using these notation of neighborhoods instead of using the modulus standard way of writing those. So this is the continuity. And now what is statement B? So if I assume, so I assume that, so we assume A. Okay, we assume that f is continuous. Now we need to prove that f inverse of A. So this is to prove that f inverse of an open set is open for every u in R. Okay. So we are assuming that f is continuous. Then we need to prove that f inverse of u is open in R for every open set u in R. So let u be an open set in R. Okay. So we need to prove that f inverse of u is open in R. So proving f inverse of u open in R, it is equivalent to say that if you take any point in f inverse of u, okay, so there exists a delta neighborhood of x naught, this whole thing contained in u, f inverse of u, sorry. Okay, so how, so we need to use these two facts. We need to use proof, we need to assume A, and we also use the fact that u is open. Okay, so if I start with x naught, which is an f inverse of u, so this thing, if I start with x naught, which is an f inverse of u, it implies that f of x naught is in u, correct? Which, and now we use that u is open. So there is a epsilon neighborhood of fx naught. Okay, this whole neighborhood, epsilon neighborhood, is contained inside u because u is open. Okay, so now we use the definition of continuity, which says that for every epsilon neighborhood of fx naught, there is a delta neighborhood of x naught, correct? So there is a delta neighborhood of x naught. In There exists a delta neighborhood of x naught such that whenever fx when f such that this whenever your fx is going to belong in this epsilon neighborhood of fx naught, uh, its pre-image, okay, this happens. So this implies what? This implies that for each x which is sitting inside this delta neighborhood of x naught, its image is sitting inside the epsilon neighborhood of fx naught, which implies that your x, this whole delta neighborhood, which I will call to be this, is contained inside f inverse of u. Okay, so f inverse of u is open. Okay, why? Because I've started with an arbitrary x naught and I have found out a delta neighborhood of x naught contained inside f inverse of u. So, which is the definition of the openness of a set? This implies that f inverse of u is open. And how do I find out the delta? I use the continuity of f to find out the delta, and the assumption that the set that I'm starting u is open. Okay, so this proves that f inverse of u is open for every open set u in R. So let me just go back to this argument once again. So we start with an open set u in R. Now we need to prove that f inverse of u is open in R. So we start with an arbitrary point x naught in the pre-image of u, and we need to show that there exists some delta neighborhood of x naught sitting inside this. Okay, this is what we need to show. Okay, so since x naught belongs to f inverse of u, you can so f of x naught belongs to u, and u is an open set. So there must be some epsilon neighborhood of fx naught which contain inside u. Okay, and now for this epsilon neighborhood, I apply the definition of continuity. So when I apply the definition of continuity, I can find out a delta neighborhood of x naught such that fx, when fx belongs to this epsilon neighborhood of fx naught, uh, so fx will belong to the delta epsilon neighborhood of fx naught whenever your x belongs to that delta neighborhood of x naught, which implies that this delta neighborhood of x naught contain inside the f inverse of u. Because if you take any point in this delta neighborhood of x naught, you apply f on it, it belongs to the epsilon neighborhood of the epsilon neighborhood of fx naught, which is contained inside u. So that means this delta neighborhood of x naught contained inside f inverse of u. And since my x naught was arbitrary, okay, since my x naught was arbitrary chosen, this x naught is arbitrary chosen, so this f inverse of u is open. Okay, so this, I'm not done yet. So this part proves that a implies b. Okay, now we need to prove b implies a. So we will start with assumption. So we will assume b. And what is b? That f inverse of u is open for every open u in R. Okay, yeah. So now what we need to prove? We need to prove a. Now what is a? That f is continuous. at, let's say, x naught. Okay, x naught in R. So what we need to say that for given so for epsilon neighborhood for epsilon neighborhood of fx naught, need to find an appropriate delta neighborhood of x naught such that x belongs to this, implies fx belongs to this thing. Okay, now what is this epsilon neighborhood? Now this epsilon neighborhood is it's an open set in R. It's open set in R. So by the assumption, if I consider its pre-image, this will be an open set in R. Okay, and clearly x naught belongs to this pre-image. Okay, so uh, there now since this is an open set and x naught belongs to this open set, so you can find out some delta neighborhood. So beta delta, you can find out some delta who of x such that you can find out some delta such that delta neighborhood of x naught is contained inside this open set. Okay, so what does it mean? It means, so for these delta, so whenever your x will be in this delta neighborhood, your fx will be in this epsilon neighborhood of fx naught. Okay, which proves the continuity, which implies that f is continuous at x naught. So I will wait for a few minutes to you guys to uh, understand this. If you have any doubt, you can ask me any questions. Okay, so since there is no question, so we are done with the step one. So we have proved that A implies B and B implies A. So this is our step one. We are done with the step one. Now let's move on to prove the step two. So in step two, uh, we need to prove that B implies C. Okay, and further, there is one more thing from step one. From this thing, we have proven that A implies B and B implies A, which implies A is equivalent to B. Okay, so we have proved that A is equivalent to B, and now we'll discuss the B implies C part. Okay, so what is B? B is uh, F inverse of U is open for every open set open U in R. Okay, F inverse of U is open for every U open in R. And what is C? C is F inverse of E is closed for every closed set E in R. Okay, so now what is a closed set? What is an open set? Uh, you have already seen the definition. I've used open set definition previously. Now closed set, its quick recall is that if it contains all of its limit point, it is closed. Okay, if a set contains all of its limit point, it is closed. Open when each for each point there exists a delta neighborhood contained inside the set, then it is an open set. Okay, so now here we use one equivalent notion. We use one fact, uh, which is A is a closed set if and only if R minus A is open. Okay, so we say a subset is closed if its complement is open. Okay, so we will use this fact in this proof. So how we will use that? So we will start with, since we need to prove, we are proving B implies C, so we need to start with a closed set E, and we need to prove that F inverse of E is closed. So let E be a closed set in R. Okay, and now to prove that F inverse of E is closed. Okay, so since E is closed by this fact, we can say it is equivalent to say that uh, R minus E is open. Okay, R minus E is open, and now we use B, which says that F inverse of an open set is also open. So this implies this thing, that F inverse of this is open. Okay, now F inverse of R minus E is open. Okay, fine. So we okay. Okay, so we have proved till this point we have proved that F inverse of R minus E is open. Now what we want to prove? We want to prove that F inverse of E is closed, which is by fact is equivalent to prove that, R minus F inverse of E is open. Okay, R minus F inverse of E is open, which is equivalent to prove this. Now we have that R F inverse of R minus E is open, and we need to prove that R minus F inverse of E is open. So now I ask this question, that is these two sets same. Okay, so this is what I ask. R minus F inverse of E, is it equal to F inverse of R minus E? So for that, again, because this is a set inequality, so we need to first prove that this part, and then we need to prove that this part. Okay, so let me write it parallelly, so it will be easier to follow. Okay, so if I start with a point which is in R minus Fe, uh, then it is in R but not in F inverse of E, correct? Okay, so so in other words, this is equivalent to say that Fx is not in E, correct? If I apply X on it, it is not in E. Okay, so now this means that um, yeah, so this means that X is in F inverse of R minus E. Okay, because Fx doesn't belongs to F inverse of E. Fx is in R, so it must be pre-image of something which is in the complement of E. Correct? It must be something which is in the complement of E. So that's what it means. So it implies that R minus F inverse of E is contained inside F inverse of R minus E. Okay. Now we got the first inequality. Now let us discuss the second part of the inequality. So we need to prove F inverse of R minus E is contained inside R inverse R minus of F inverse of E. So again we follow a similar approach. We start with a point F inverse of R minus E. Okay, so which is same as to say that F x belongs to R minus E. Okay, which is similar to say that Fx belongs to R, which is equal to say that Fx doesn't belongs to E. Okay, in other words, X doesn't belongs to F inverse of E. Okay, which implies that Fx belongs to this thing, giving us this inequality that okay. Now from 1 and 2 we get the uh, desired equality between the set that is equal to F inverse of R minus E. Okay, now what is the power of this equality? The power of this equality is that uh, we can use the fact that because these two are equal sets, so if this is open, then this is open. Okay, um, so we had So we had this. Uh, so we had this open. F inverse of R minus E was open, and now from the previous discussion, just we discussed, we know that it is equivalent to say that R minus F inverse of E is open because these two sets are equal, which implies that F inverse of E is closed. Okay, so this proves B implies C. Now, uh, we follow the similar argument. Um, so we'll write down the proof of C implying B. C implying B here. So what is C? So we assume that um, F inverse of E is closed if E is closed in R. Okay. So this is we have assumed, and now we also assume let U be an open set in R. So you need to now we assume that let U be an open set in R. So you need to prove that F inverse of U is open in R. So this is what you need to uh, prove. Okay. So you need to prove that F inverse of U is open in R. So now this being open in R is equivalent to say that R minus U is closed. Okay. R minus U is closed implies from this C fact, from C, that F inverse of R minus U is closed. Okay. Now we know that F inverse of R minus U is equal to R minus F inverse of U from the fact that we just proved below. So this implies that this is closed. Now which proves that F inverse of U is open. So altogether it implies, altogether it proves, if I assume C to be true, then B is true, and this completes the proof. So as a result, we have proved B implies C
Sir,
and
what was the question, sir?
C implying B. Altogether, we have proved that B and C both are equivalent statements, and as a result, just wait for a second. As a result, A implies A is equivalent to B and B is equivalent to C. Hence, all three statements are equivalent. So this is the question that we were proving. So we used, so we broke it into three steps: first, second, third. So first we proved that A is equivalent to B. Then in the second step we proved that B is equivalent to C. In the third step we proved we use the fact that if A is equivalent to B and B is equivalent to C, then A, B, C all are equivalent to each other. Okay.
Hello, sir.
Yes. So Ravi, you can do one more thing. So I'm recording this session. You can go back to the YouTube channel Maths with Prerak P on YouTube, and you will find this recording by tomorrow morning. So I don't need to uh, again go through this solution of this question. So you can do that. So I've discussed this question thoroughly. So you can go back to the YouTube channel tomorrow morning. You okay? So let me write down the. So this is the YouTube channel that I'm referring to. Maths with Prerak. Prerak is my name. So you can go to this channel and you can find the recording of this session. Okay. Okay. Now let's move on to discuss this question number 2. So in this question, you need to prove whether it is true or false. Uh, you have given a function from a real valued function on a real variable such that the preimage of a compact set is compact for every compact set. Now this statement is then f is continuous. So you need to say that whether this statement is true or false. So what do you think? Is it true or is it false? So again, we repeat. So if it is true, no, a set can't be continuous. What do you mean by a set being continuous? A function is continuous. Set can't be continuous. It doesn't make sense to say that set is a continuous. Okay, so function is a continuous thing, but set can't be continuous. So again, if you think that the answer is true, you need to give me an argument, and if you think it is false, you need to come up with an example. Okay, so I will I will tell you what it is. So um, yeah. So in question you are asked to prove that. So first of all, this is false. Okay, and I will give you an example uh, where the function is assumed to be continuous, but the preimage of a compact set is not compact. There are multiple examples. I will give you one of the example. I will discuss all of the examples with you. So in order to disprove this statement, you need to come up with a continuous function f such that preimage preimage of compact set is not compact, so that for some uh, compact k, its preimage under the map is not compact. Okay, so yeah, so let me draw the graph. It will be easier for you guys to understand. So if I can't understand that statement. um, what if fk was given instead of f inverse of k? Acha, okay, you are asking in the statement if I switch the position of fk and f inverse of k. So you are saying that if f of k is compact for every k is then also it's not true. In either case, it's not true. Okay, it's going to be false in either of the cases, because continuous function means continuous function is so we have examples of continuous function for which if you start with the compact set and its image is not going to be compact, it need not to be compact. Okay, similarly if you take a compact set in the range and you consider its preimage, that is not going to be compact. So we have an example for both of the cases. So I will, so since I'm giving an example according to the question, that if I start with the if I start I'm giving you an example of a continuous function uh, and a compact set k on the range such that its preimage is not compact. Okay, so one example is this constant function. If you consider your fx to be 1, Okay, so if you consider your image of the function to be 1, fx to be 1 for all x in R. So this is a symbol for all, if you are not familiar with. Yeah. So this is the graph for uh, fx equal to 1 constant function. Now, 1, so if you consider this singleton in R, okay, if you consider this singleton R, so this is a compact set. This is compact in R. Why? Because it is one singleton 1 is closed and bounded. So bounded in R. So any closed and bounded set in R is compact. So one is singleton 1 is a compact set in R. Now if you consider its pre-image of 1. Now pre-image of 1 is whole of R. Okay, because it's a constant set. So its pre-image contains whole line R. So uh, yeah, so pre-image of compact set is not compact. Okay, so this is an example. This is example number A. Is this example clear? Yes,
Yeah,
because R is not compact.
hello, sir.
Correct.
Hello,
Another
sir.
example. Uh, so this example is kind of like a trivial example. Let me discuss something which is non-trivial, and a function which you all guys are familiar with. Also, um, so again, I'm going to draw this function. Yeah. So I hope you all of you can recognize this function.
Hello, sir.
Yes. So this is a sine function, sine of x. Okay. Um, and now we all know that sine of x takes values between -1 to 1. Okay. So what if I take just, if I consider my compact set to be singleton 1, or let's say singleton 0 in R. So this set is compact because singletons are compact. Okay, that we know. But what is the pre-image of this set? So what is sine inverse of 0? Sine inverse of 0 is multiple of pi. Okay, where k runs over integer. So sine inverse pre-image is these points. So whenever this function hits the x-axis, it's going to be pre-image. Okay, so this set k pi, so this set sine inverse of 0 is not compact. Okay, why? Because it's not bounded. Okay, so this set is not compact. Sine inverse of 0 is not compact. So this is another example of a continuous function whose uh, of continuous function and a compact set whose pre-image is not compact. Okay, so I think these two examples are enough for you to understand the behavior of a continuity and why this statement is not true. Any question in that? So then for this function it will be true, but what if I take any other function? Okay, So in that case that you are considering, so I will take some another function for which the image of compact is not going to be compact. Okay. So yeah. Okay, now let's discuss this question number 3. Okay, so I'm leaving this question number 3 as an exercise for you. So you need to come up with an example. I can tell this is false. Okay, this is what this hint I am giving to you. You need to come up with an example of a continuous function. You need to come up with an example of a uniform continuous function such that you can function on this open interval a comma b such that its extension such that f can't be extended to this uniformly. Okay, so I leave this as an exercise for you to think about this question. Okay, now let us discuss this question number 4. Yeah, that's what I'm leaving to you guys to think. So I'm not telling you an example. You need to come up with an example of a uniform continuous function whose uh, whose extension can't be uniform continuous. Okay, I'm leaving this that as an exercise for you. Maybe next session, I will discuss. In the next session, I may discuss the solution to that question as well. Okay. Okay. Now question number 4. So you need to choose the most appropriate single choice. Function is a real valued function on a real variable, such that that function satisfies this inequality. Okay. Now we need to choose the most appropriate single choices. First is it continuous function. Second is that if you define a function yn recursively, then is it a convergent sequence. Third is that if does there exist a point x star in R such that f is fixed on it. Okay, and does that x star unique. Okay, so we will prove one by one. So we will start with the statement number 1. Okay, so we have a function f satisfying this inequality. Okay, so a part we need to prove that f is continuous. Okay, so we need to prove that f is continuous. That means for every epsilon you need to give me for given epsilon greater than 0, uh, we need to find out a delta such that fx minus fy smaller than epsilon whenever your x minus y is smaller than delta. Okay, so how do we do that? So for that, let us start with this inequality. Okay, which is 2 times of x minus y. Now we want this to be smaller than epsilon so that this fx minus fy can be smaller than epsilon. Okay, so we want this thing to be smaller than epsilon. So what we do, we consider this part only. Now you consider this part only. So this part gives you this thing, which further gives you this to be smaller than epsilon by 2. Now you choose this epsilon by 2 to be your delta. Okay, so what happens? So when your x minus y is going to be smaller than delta, then fx minus fy is going to be smaller than 2 times x minus y, correct, because of the inequality. And now this is going to be smaller than 2 times delta, which is going to be epsilon. So your fx minus fy is going to be smaller than delta. So is this does it make sense? Does the argument make sense? So it proves that f is continuous um, for f is continuous at x, and x was chosen arbitrarily, so x is continuous for all x in R. Okay. Can mod over x minus y equals delta? That can be equal to, that can not be equal to, it's fine. So you can take, you can remove this inequality, it is completely fine. Okay, it still makes sense. Okay, so this is continuous, uh, and this, I think every argument makes sense to all of you. So the a part is true. Okay, so we can choose this part. So a is true. Now what about b? So b is quite interesting. So b is asking you to construct a sequence recursively. So it is defining your first point to be x naught, uh, first or zeroth. Oh, zeroth. So y naught is fx naught, y1 is going to be, and yn is f acting on yn minus 1, correct? So in other words, yn will be, so y1 will be f on y naught, which will be f on f of x naught, which is f square on x naught, correct? So this implies that yn will be n plus 1 n plus 1 by f to the power n plus 1 of x naught. Okay, so now uh, if you construct such a sequence, then does this converge? This is your question now. Okay, so for that, uh, I'm saying, like, this is not going to true for whatever function you choose. It very much depends on the function that you are choosing. Okay, so let me give you an example. So for example, if you take if you take this function uh, fx to be 2x, okay, if you take this function, so clearly this function satisfies the inequality given in the question. What's the inequality? Inequality was fx minus fy, this modulus is smaller than or equal to 2 times y minus xy, and it is 2x minus 2y, which is equal to 2 can be taken out, and this, which is more than or equal to 2 times of x minus 5. So this function satisfies the inequality, hence this function satisfies the hypothesis of the question. Now if you try to construct the sequence yn, so y naught will be 2x naught, okay, yn will be 2 to the power n plus 1 x naught, okay, 2 to the power n plus 1 x naught. Now clearly this sequence, okay, now you choose x naught, also you choose your x naught to be, choose x naught to be 1. So what does this function become? So this so if you choose x naught to be 1, your yn becomes 2 to the power n plus 1, okay, and this sequence does not, this sequence goes to infinity as n tends to infinity, okay, and this goes much faster than as n tends to infinity. So this is a non-convergent sequence, okay, so this doesn't converge, so does not converge. So in other words, this b part is not true, okay, it very much depends on the function you are choosing, it very much depends on the x naught that you are choosing, okay. So so on the left hand side I am constructing the sequence, so this sequence will look like in this general term, to be yn equal to fn plus 1 of x naught. Okay, now the question is, does that yn converge? So I take a function to be 2x. Okay, now this function needs to satisfy the inequality given in the question. So it is satisfying the inequality given in the question because you can take 2 common out and it is satisfying the inequality given in the question. Now once it satisfies the inequality, you rewrite your sequence will be yn equal to this. If you just repeat this process which I did in the left, either your yn sequence will look like 2 to the power n plus 1 times x naught. Now this x naught you can choose arbitrarily also. So in my case, I'm choosing it to be 1 so that the example will make more sense. Okay, because I want to give a counter example to the to b. So now if I take my x naught to be 1, my sequence becomes 2n plus 1, 2 to the power n plus 1, and 2 to the power n plus 1 tends to infinity as n goes to infinity. Okay, as you start taking larger and larger value of n, the 2 to the power n plus 1 will also start taking larger and larger value. Okay, it is an increasing sequence, it is monotonous increasing sequence, and monotonous increasing sequence does not converge because it's not bounded. Suppose if it's converge, then it has to be bounded, but this sequence doesn't uh, is not bounded, so it can't converge. Okay, so that's how we prove that it's not a convergent sequence. Is this clear? Okay, very good. Okay, now C part. Um, so in C part, it is saying that there exists some x star in R such that f of x star is equal to x star. So basically, it is saying that there exists some fixed point of f. Okay, so we say that there is no fixed point. Okay, so for that, what we need to do, we need to come up with an example function which satisfies the hypothesis. So let us take fx to be identity function which is x for all x in R. Okay, if I take this function, so clearly fx minus fy, which is equal to x minus y, and is smaller than 2 times x minus y. Okay, so this inequality is satisfied. So the hypothesis of the function is satisfied. Okay, correct. Now, now in this function, oh sorry, yeah, if I take it to be constant, let's take it to 2. Okay, this is a constant function. Okay, clearly this is equal to 0. Okay, fx minus fy is equal to 0, which is which is which is larger, which is smaller than 2 times x minus y. Okay, so because this is a positive value, it always has to be greater than this thing. So this is fine. The inequality of the question satisfies. So now this, oh, this is also not a good example because it has one fixed point. So let me take this example, which is uh, 2 times x. Okay, this will be a good example. So again, 2 times x, I'm taking the similar function uh, which I took earlier. So this is clearly equal to this, satisfying the inequality. Now this function fx doesn't have any, does not have any fixed point. What do we mean by that? That there is no x star such that this is equal to x star. Okay. So if suppose if that happens, so that means 2x needs to be equal to x. Oh, it has 0 in that. So let us take plus 1 then. Oh, that will also have a solution. Oh, okay. Oh, okay. So if I take any linear function, um, ax plus b equal to x, so it will always have a solution, because I can take a minus 1 b, and this will be always be the solution to that. So this will always be the x star. So I can't take any linear function. Okay. So the function needs to be something which is not linear. Hmm. Okay. So I don't know the. Okay. So clearly I haven't thought much about this part. I will discuss this question next time. Okay. Yeah. So I will discuss this part and the next part next time. So as of now, I don't have any example which directly contradicts these two facts. If you have any example, you can tell me. I don't have any example right now. So in the next time, I will come up with an example and I will uh, try to disprove this fact. Um, yeah. So any questions till now? Whatever I've discussed, any question there? Good. So I will. So we will meet next time, same time, uh, Monday, 7 to 9. Same link will work. Um, and the recordings will be available on the YouTube channel Maths with Prerak, earlier, as I have mentioned earlier as well. So you can go to that and you can check out the check out today's video, previous recording session as well. Okay. If there is no any, if there is no doubt, so Ravi, I suggest you to just go back to the YouTube channel. You can have a look at it. I discussed a few examples. Basically, I calculate a few limits of functions. So um, I it wouldn't be possible for me to do that again. So you can go back to that channel. You can see the recording. That will be fine. If you have any doubt in that part, in the first part, you can again ask me in the next session, next Monday. Okay. Okay. See you guys then. Uh, no, you can ask me directly next time, next Monday. Instead of asking on the discussion forum, you can ask me directly next Monday, because you anyway will be joining. Correct.